Steinhauer here, and welcome back. And this is an exciting video because we finally get to talk about my favorite diagram in all of science, the Hertzsprung-Russell diagram. And these are extremely important because they give us huge amounts of information about how stars work and classify them and sort them and give us insights about stellar evolution and all sorts of good things. They are extremely important. Think the periodic table of importance in astronomy. What is a Hertzsprung-Russell diagram? Well, it's named after two astronomers, Ejnar Hertzsprung and Henry Norris Russell, who independently in the early 1900s made a plot like this of stars in the nearby universe and almost immediately realized how important it was. So what is it? Well, it's a graph that plots luminosity on the y-axis. Here we go, luminosity. And it plots surface temperature on the x-axis. You'll notice this is solar luminosities here, one being the sun, all the way up to 1 million times more luminous than the sun, to 1 million times less luminous than the sun. This is a huge range in luminosities here, and it's in a log scale. Almost always, either absolute magnitude or log luminosity, either one works fine. And the y-axis, but bright is on top and faint is on, more luminous is on top and less luminous is on the bottom. The x-axis is surface temperature, and you can see the familiar OBAF-GKM spectral classification sequence here. But you'll notice that does something weird, right? If you want to plot this as surface temperature, it makes this plot backwards. The hot stars are on the left and the cool stars are on the right. Again, this is weird. Normally, you can see the surface temperature down here too, 30,000 Kelvin, 10,000, 6,000, 3,000 Kelvin. You wouldn't normally want to do this. You'd want to plot surface temperature in the other direction, but this is how I think both Hertzsprung and Russell did their original diagrams. And they were using the spectral classification scheme to do this. And OBAF-GKM going in that direction for them made them plot it in this direction, and that's backwards in temperature. This is how it's always been done. This is how astronomers see this diagram. If you were to go to an astronomy conference and put up a HR diagram with the x-axis in the other direction, you'd be booed off the stage. This is how all Hertzsprung-Russell diagrams are drawn now, are plotted. Because that's the way all astronomers are taught to think about it. So just be aware, the x-axis is backwards. So hot temperatures are on the left, cool temperatures are on the right. Okay, why is this such a useful diagram? Well, let's remember the luminosity equation. The luminosity equation, remember, was luminosity is 4 pi r squared sigma t to the 4th power, right? And the 4 and the pi and the sigma are all constants. So this is really luminosity is proportional to r squared t to the 4th. Okay, great. So the cool thing about this diagram is we've got two of these parameters explicitly plotted on this diagram. We're plotting the luminosity versus the temperature. So this is giving us radius information also. Let's try to see how that works. Let's say, so here we have some things on this diagram. The first thing is it's the same diagram as we had before. Luminosity is on the y-axis, spectral type or surface temperatures on the x-axis, going in the way we expect it to go. But now we've plotted some actual stars on this diagram as well. You can see a line we've drawn through here, a bunch of stars up here in the upper right, some stars down here in the lower left. But there's the sun. Let me point out the sun. The sun is right here on the diagram, right? It's about in the middle. It's kind of a normal star. So let's imagine starting at the sun and moving in a direction on this diagram. What's going to happen as we move in a particular direction on the diagram? Let's say, for instance, we want to move up on the diagram. So we're starting at the sun and we're moving up. What does that mean for this equation? Moving up on this diagram is increasing the luminosity while keeping the temperature constant, right? So L is going up and temperature is not changing. What must that be? How must radius be changing? What must be happening to the radius as we move from the sun up on this diagram? Well, you should think of equations like balance scales, right? If you do something to one side of the equation, you have to do the same thing to the other side of the equation. So if the luminosity is getting bigger and temperature isn't changing, what has to be the case of the radius? The 4 and the pi and the sigma aren't changing. The only thing that can change, the only way to make this side bigger is to make this side bigger too. And the only thing we've got left to make bigger is the radius. So moving up on the diagram, implies that it must be the case that the radius is increasing also. If you're increasing the luminosity without increasing the temperature, then the radius must also increase. How about if we move to the right on the diagram? What's happening there? Well, if we move to the right from the sun on the diagram, what happens? The luminosity is now staying constant because we're moving straight right, but what's happening to the temperature of that object? It's getting smaller. The temperature is going down as the luminosity is staying constant. Let's try to figure out from our equation what's happening. Again, the luminosity is not changing. The left-hand side of this equation is staying exactly the same. That means the right side also has to stay the same. And if we're making the temperature go down, what does that mean must be happening to the radius? It has to be going up to compensate. If the whole side of that balance scale is staying the same and you're making one of them smaller, you have to make one of the other, something else in there bigger. And radius is the only other thing on that side that we can make bigger. So it's also true that if you move to the right on this diagram, the radius, the physical size of your star, must also be going up. So moving to the right and up on this diagram means you're moving towards larger physical stars. Moving down and to the left on this diagram means you're moving to smaller physical objects. So one of the reasons why the HR diagram is so important is they're all three fundamental parameters of stars, or three of the fundamental parameters of stars, luminosity, radius, and temperature, are all indicated for objects that you plot on it. And that's really cool. So you can already tell a star like Aldebaran, a star like Antares, these must be physically much larger stars than the sun. Why? Because they're both up on the diagram, which means they must be larger, and they're to the right on the diagram than the sun, both of which must mean that the physical size of the stars are going up and up and up. Okay, there are lots of interesting parts of this diagram. I'm going to show a video of how this diagram is created for a globular cluster. In fact, pause this video right now, go down below to the supplemental videos and watch the video on constructing an HR diagram. I think it's really instructive to see how those kinds of diagrams come together. We're not going to talk about a globular cluster until later on, but the HR diagrams, the Hertzsprung-Russell diagrams of globular clusters are so important. It's worth taking some time to do that right now. Okay, let's talk now about some features of the HR diagram. If you just take a census of all of the local stars in the galaxy and plot them all on the HR diagram, luminosity versus surface temperature, 90% of them will fall in a fairly straight line from hot and bright. So again, the upper left-hand corner of this diagram is the most luminous stars and the hottest stars, all the way down to the lowest temperature and lowest luminosity stars down here in the lower right. And not surprisingly, we're not all that creative as astronomers. What do we call the region of the diagram where 90% of the stars are? We call it the main sequence. That's most of the stars in the galaxy, falling along this sequence from hot and luminous to cool and very dim. The sun, being right here, is right on the main sequence. The sun is a main sequence star, one of most of the stars in the galaxy. So you'll see other stars like Proxima Centauri, the closest star to us, star named Spica and Sirius, and lots of other stars falling right on the main sequence. Now, we know that stars that appear above the main sequence, we call those giants and supergiants. Why? They must be physically larger than the stars that are on the main sequence, right? Up and to the right both imply larger. And so stars that are up and to the right, or even just up or to the right, must be larger than their main sequence counterparts. So we call those giants. And if they're way up at the top of the diagram, we call those supergiant stars. Conversely, those stars that appear way down here, we call them white dwarfs. By the way, this is a little confusing because sometimes people will refer to main sequence stars as dwarfs, but white dwarfs specifically are these very, very faint, very hot objects that appear much lower, much below and to the left of the main sequence. And those must be much, much smaller than their main sequence counterparts, right? The giants must be much, much larger than the sun. These white dwarfs down here must be much, much smaller than the sun. And we can pick that out just by looking at these stars and where they appear on the diagram. Okay, we actually can classify stars also based on whether they appear on the main sequence or not. And you can sort of see the diagram here. The main sequence stars are here in blue. And the location and we call this spectral class, these are spectral luminosity classifications, I should say. Luminosity class Roman numeral 5 are all the main sequence stars. And so this is a little bit confusing, right? Because luminosity classification, you want them to be a specific luminosity. But for luminosity class 5, there's a huge range in the actual luminosities of those stars. Really what this is giving us is how far above the main sequence is this star at the particular temperature that it is, right? So all stars that are on the main sequence are luminosity class 5. And then how far above the main sequence they appear will give them a Roman numeral based on where they appear in the diagram. We usually leave white dwarfs off of this diagram and only do 1 through 5 based on where they appear in this diagram. So here's the full luminosity classification. The ones are at the top. Again, this is a little bit backwards because the smaller the number, the more luminous the star is at a given temperature. But ones are supergiants. 2s are bright giants. 3s are just giants. 4s are subgiants. And 5s are main sequence stars. And sometimes you'll see these referred to as dwarfs. Although not to be confused with white dwarfs, which are well below the main sequence. So that gets a little bit confusing. So the sun's full spectral classification, we already said that it was a G2 star. That's its spectral classification, but we can also include its luminosity classification, which is Roman numeral 5. So G25 is the sun's full luminosity, full spectral classification, both spectral class and luminosity class. Sirius, for instance, is an A1 dwarf. It's a main sequence star, which is much hotter than the sun. Proxima Centauri, we saw it down there, is an M5.5. Sometimes the luminosity classes will be subdivided into half spectral class, half subclasses. And it's a main sequence star 5 also. And then Betelgeuse, we already said that was an M2 star, but it is an M2 supergiant. It is an M2 at the top of the HR diagram. Okay, so why is this so important? The HR diagram gives us spectral temperature. It gives us color. It gives us spectral type. It gives us luminosity, and it gives us radius. And we'll see how it can give us things like stellar evolutionary status, where a star is on the evolutionary sequence, and even how it can give us the ages of specific stars in clusters. And for all of those reasons, it's a very, very important diagram. Okay, let's take a short minute now and test your knowledge of the HR diagram and where things fall on it. So here's a series of questions that are just designed to help codify this concept of an HR diagram and where things are on it. You ready? Let's go. So here we have an HR diagram, and we've got 4 stars indicated on it: star A, star B, star C, and star D. I want to know which of these stars is the hottest. Go ahead and write an answer down. Pause the video if you need to. Okay, which stars of these is the hottest? And again, you can tell just by looking at where these stars are in the diagram. Temperature is the x-axis of this diagram, right? The hotter stars are on the left, the cooler stars are on the right. The distance left or right on this diagram is the only thing that matters when you're talking about stellar temperature. The star that's furthest to the left is going to be the hottest. That has to be A. The star that's furthest to the right has to be the coolest, and that's star C. Doesn't matter how far up or down they are on the diagram, only thing that matters is left, right. Which star is the most luminous? Again, take your pick. Well, the y-axis is our luminosity. So the star that's the furthest up on this diagram must be the most luminous. Which one is that? That's star C, which is just a little bit more luminous than star B, but way more luminous than star D and way more luminous than star A. So again, how far up and down you are on this diagram is entirely indicative of how luminous you are as a star. Okay, which star has the largest radius, which is physically the largest in size? Make your guess. All right, well, how can we tell? Well, maybe you can see in the background, there's actually some lines of constant radius, but we should be able to tell just by looking at where these stars are on the HR diagram, right? The further right you are, the bigger you are, and the further up you are, the bigger you are. So the star that is furthest to the right and up on the diagram must be the largest. C has to be the largest radius object of any of them that I've plotted here. And A must be the smallest because it's below and to the left of all the other objects that I've plotted. Okay, so we'll stop there and then come back and talk about what it means to be in different parts of the HR diagram and why some stars appear in different places. Okay, see you then.